should
Mhm.
should give you all the background information. So did you have any questions that came up from yesterday?
Mm, no.
Okay, that's fine. Let's see. Few slides. So we will just go ahead and get started.
Mhm.
Okay. So yesterday, I think we finished this slide. We finished storage. We talked a little bit about IFPS, which is the interplanet. Yeah,
Mhm.
I spelled that wrong.
Yeah,
Interplanetary file system. So it should be not IFPS,
IPFS.
IPFS. Yep, there we go. So that's discussed in the document. Just to explain it briefly, it's a sort of decentralized storage, which is not a blockchain per se, but it works similar to BitTorrent, and it's meant to store the actual hard data of NFTs, and then the metadata pertaining to ownership and things of that nature and transaction history and stuff that is stored on the blockchain.
Mhm.
So that's just IPFS in a nutshell. So when they made IPFS, they came up with a routing system and a network discussion slash discovery, which is lib p2p, the peer-to-peer library, and so that has been adapted for other uses,
Mhm.
and it's the primary way that nodes speak to each other on flow is with lib p2p, and it comes from IPFS.
Okay. But I
Question.
read like somewhere this the peer-to-peer or IPFS. I think like it can work in any other thing as well. Like not only the peer-to-peer, right?
What do you mean?
Means like the IPFS. It is not like exclusive for peer-to-peer communication. Means like the peer-to-peer may work even without the IPFS, or IPFS like works independent of the peer-to-peer, something like that. It was in the architecture document. Maybe I'll go through.
That's fine. So this is the IPFS website.
Uh-huh.
Um, it's all peer-to-peer, a peer-to-peer
Okay.
hypermedia protocol designed to preserve and grow humanity's knowledge. And so you can take a look at it here.
Hmm.
You can see it has a Go implementation.
Okay.
So the P2P. And it runs off of libp2p. They
Hmm.
invented libp2p specifically for IPFS. So you can see that they
Okay.
have the libp2p documents right here.
Uh-huh.
More about libp2p. Right. Yeah, there might be a mistake. If you see a mistake in the document, just let me know and I can fix it.
Okay. Okay. Sure. I'll let you know like
Yeah, if you see somewhere where it's not accurate or
mhm.
it's confusing or something, what is this stuff?
Sure. Sure.
Okay. Oop. Um, Give me 1 second. Zoom is acting weird. Okay, there we go. Okay. Oh, no, that's not what I want to do. Why is it doing that? Okay. Here we go. Any other questions about storage?
No.
Okay. So we're going to talk about nodes. So a node in blockchain is just any device which is connected to a network. And so there's different kinds of nodes. And a node is a very similar concept to a network peer, but they're slightly different. So a node is any device which is connected to a network. A network peer is a node on the network which can directly communicate with other nodes and has full functionality. So there's different kinds of nodes. There's nodes that just redistribute information. There's nodes that
Mhm.
serve as an endpoint for communications. They just receive information. There's nodes which
Okay.
act as full clients, or I mean, which act as clients, and there's ones that act as full servers. So there's two major kinds of nodes in blockchain: full nodes and lightweight nodes. The full nodes implement all the blockchain rules and they're the backbone of the network. The lightweight nodes are usually on the network because they want to benefit either from watching the protocol happen or from getting information or something of that nature. So the network, a network peer, it says a computer system connected to one another over the internet in a peer-to-peer network. This is basically a full node, and they directly share files without the need of a server in between them. And every network pair is both a file server and a client. Questions here? I think this is you should be
Yeah.
familiar with this to a certain extent. Okay. So let's look more at the different kinds of nodes. There's full nodes and what the nodes do on the network. There's full nodes, lightweight nodes, mining nodes, and staking nodes. A full node is basically a server, and it helps to maintain the consensus between all the other nodes. They verify transactions, they store the entire blockchain, and not every full node has to store the entire blockchain. Some of them only store it to a particular point in time. And storing the state of the blockchain from a particular point in time is called a spork. So that's
Mhm.
an important thing to remember. If you only have it up to a certain period of time, that period of time you have it up to is called a spork. Otherwise, they have
Okay.
the full blockchain. Lightweight
So,
nodes,
like, what
yeah.
is consensus?
Well, don't worry.
Uh,
We'll talk about
okay.
that next slide right here. We'll get to
Okay.
exactly what is
Okay.
consensus.
Okay.
Excuse me. So the lightweight nodes, they act as clients, and they really require the full nodes to get information or to do much else, and they don't
Mm.
store a copy of the entire blockchain. Then you have mining nodes and staking nodes. A mining node can be a full node or a light node, but the purpose of a mining node is to create blocks in what's called proof of work, which we'll talk about in the next one. Then we have a staking node. A staking node is also a full node, and it puts the contents of its wallet um, in jeopardy or as a stake as part of proof of stake. So we'll talk about proof of work and proof of stake in the next slide.
Oh,
Questions?
no questions. Yeah.
Okay, so now we're going to talk about consensus.
Yeah.
Consensus and verification in blockchains, this is how we ensure data validity. So obviously, if you have all of these nodes, which are geographically distributed, there is no centralized authority. How do we know that everybody is sending valid data to the network, and also that everybody has the most up-to-date valid copy of all of the data? How can we ensure this? Well, there's a concept in blockchains called consensus. So what is consensus? Consensus is the mechanism by which all of the nodes of the network agree as to the validity of data, and they verify the transactions. And so the purpose of consensus is to make sure that all the nodes are synchronized with each other and they agree on the validity of the transactions. And one of the main principles of this is called the longest chain rule. So every block on the blockchain is sequentially ordered, meaning you can never have a new block which is added without the previous block. And every new block only consists of transactions which were never added before. So it's impossible to miss a block or to add two blocks at the same time because because they require and ancestry of hashes, which we'll talk about, Merkle trees. But basically, that means that whoever has the most blocks, that's the most updated information, because it's not possible to be participating on the network and have a different kind or different set of information. So nodes always follow the longest chain. And any node which is broadcasting invalid information is not going to affect the network, because that data is going to be rejected, because it's not going to follow the longest chain rule. And ultimately, the hashes will begin to be different over time if it's not based on the exact series of previous blocks. And so that is a concept called Merkle root. So we'll talk about
What
that.
is its longest chain rule?
Longest chain rule.
What it is that the Merkle?
Yeah, so the longest chain rule is that every node accepts the version of the blockchain or the database which has the most blocks on it, because it assumes that that is the most up-to-date information.
Okay.
And the way that you know the blocks are in the right order and that the longest chain is valid is through something called Merkle tree, but we'll talk about that in 2 slides.
Oh.
Okay. So the primary way that consensus is done is through algorithms. It's not the only way, but it's one of the primary ways. So you have simplified Byzantine fault tolerance, delegated Byzantine fault tolerance, and practical Byzantine fault tolerance. Those are all 3 different algorithms. So they're called the Byzantine. The reason why they're called Byzantine is because this is in reference to the Roman Empire. So this is a classical cryptography problem. In the Roman Empire, if you have one general over here and he's fighting in the army, and then you got another one in this country over here in another country, and you got another one in this country over here, and they're all fighting, how do they update each other fast enough so that everybody knows what everybody else is doing so that they can coordinate? That's called the problem of the Byzantine generals. So there are various algorithms which they use to try to go through that problem. The 2 most important ones are proof of work and proof of stake. Proof of work is a way to do consensus using miners. So the way that proof of work works is that you have miners on the network, and their job is to collect the transactions, form them into pages, and use their processing power to validate all the transactions. And they guess the nonce brute force randomly in the process of doing that. And then when they get it, they get rewarded. So the consensus is happening here using processing power. And as the network grows, it becomes more difficult and requires more processing power. Proof of stake is the second one, and that's what Ethereum uses. And that's what Flow uses to a certain extent. So Flow uses both a consensus algorithm and a consensus node. So what does proof of stake do? In proof of stake, the algorithm randomly chooses a node on the network. So you sign up to be a full node on the Ethereum network. The algorithm is randomly going to choose one of the full nodes, and it's going to select them. And it's going to say, all of your money, all of your ether, we're going to hold it. You can't use it. If you do any malicious behavior, which is going to harm consensus, then we're going to take your ether. If you let us use your node in order to validate the transactions and get the most updated thing and commit a block, then we will give you some of the transaction fees as a reward. So the punishment would be you would lose all of your ether. The reward you would get transaction fees. So randomly chosen person is rewarded for block validation if the block they mine is legitimate. If they perform malicious activity, their ether are seized. And you get more reward the more you have in your wallet, which is at risk, which is staked. That's why it's proof of stake. So the more that you have in your wallet, the more that you get as a benefit. So rich people become richer in proof of stake. And the validating
Okay.
capacity depends on the stake within the network. In order for somebody to hack this kind of blockchain, you would have to own 51% of the cryptocurrency that is on there. Otherwise, you won't be able to. So if somebody wanted to hack Ethereum blockchain and put fraudulent transactions, they would have to already own 51% of the Ether.
Hmm.
Questions about this?
Yeah. So you told like whatever we have in the wallet, uh, all will be like regarded as a transaction fee if it is legitimate. Otherwise, all will be lost, right? If they perform any malicious activity.
Yeah, if you do any malicious activity, all of your
Uh-huh.
Ether will be confiscated by the
Hmm.
network. It'll be taken from you. But if you don't, like you said, you'll benefit from transaction fees.
So even like whatever they own, all will be staked.
Sorry?
Like for example, if I own Ether, certain amount of Ether, even that also will be staked, or only like which related to the transaction fee will be
So
staked.
everything that is in your wallet will be staked.
Oh,
Whole account balance.
zero balance.
Yeah, your entire general balance is going to be staked if you get
Hmm.
selected to mine a block.
Mm-hmm. Okay.
So you're at risk of losing all of your assets if you do something bad. But if you
Okay.
just let it mine, then you will receive a reward which is proportional to that.
Okay. Got it. That's why it is called. Okay. Oh, it makes sense. Yeah. We can go to the next.
You ready?
Yeah.
Okay. So some people consider proof of stake to be the most important kind of consensus. The stake is divided entirely between stakeholders and is based on a reputation system, based on the amount of tokens that you own, cryptocurrency, which is your status in the market. The owner of the block is determined based on the block wealth, and there's no rewards from mining the block. The digital currencies are issued at the beginning, but there's the transaction fees for the miners. In this kind of a situation, the rich become rich and the poor become poor, and it requires you to buy into the platform if you want to participate in it. And it was specifically designed to deal with some of the issues of proof of work. All the miners are randomly chosen, and you have to have a certain amount of tokens in your wallet to even mine in the first place. Otherwise, you won't even be considered. And so the miners take transaction fees, and in Ethereum, they're called forgers. Any questions about this? It's just kind of a summary of the previous slide.
Oh.
Okay. So the Merkle tree, what is a Merkle tree? Merkle tree, so we talked about how each block, it has a block header and it has the hashes, which is a summary of all of the transactions which are on there, and it has the nonce for the miners to guess. So what they came up with something called Merkle trees.
Mm.
What a Merkle tree does is you already have the hash, which is almost like a summary of all the transactions on the block. It's like a digest. But what if every new hash for every new block contains the previous hash of the previous block? So you not only are hashing all the transactions, but you're also going to include the hash of the previous block. And so you have to have an even amount of transactions to do that. But when you do that, then that means that the hash of every subsequent block, it has to be in the right order. Every transaction now will have to be in the right order. And if any single one is not, it will disturb the Merkle tree hash. So this lets you directly see the exact way and the chain of every blocks in the exact order that's supposed to be. So the first block, the Genesis block, it doesn't actually have a hash of a previous block because it's the first one, obviously. But transactions are tracked from there, and that's day 0. And then every new block reflects these updated transactions. So the purpose of the Merkle tree is secure verification and efficient content in a large body of data. So you have the Merkle root. The Merkle root is the basis of the hash tree. Then when you hash all of that, you get a summary of all the data in the block, which is like a digital fingerprint of all the transactions. And then you keep hashing that with each subsequent block, and you get a hash-based data structure where you have the root and then leaf nodes, and you just keep hashing the node pairs until only one hash is there, and that's the Merkle root. So every leaf node is a hash of transactional data. Every non-leaf node is a hash of that one, which is a hash of previous hashes. And so it's done in factors of 2, and each node has up to 2 children. And it comes from a bottom-up fashion from individual transaction hashes. And it's written in binary. It has to be even number of transactions because it's in Boolean. If the transactions are odd, the last will be duplicated to be even. All the data inputs are grouped into pairs. An odd number requires the last one to be paired with itself after duplication. It applies to all transaction IDs run onto the block. All transactions are grouped in pairs, then hashed, paired, then hashed again until only one remains. And then this is stored in the block header. So you have your first block right here. This is your first block. And you go ahead and you hash all the data of the block, and you get a digest, and you put it at the top of the block. Then you make a second block, and you hash all of the data on this block. But then you include a hash of the previous block's data.
Mm-hmm.
And then you hash them both. And now you have a leaf hash. Now somebody tries to change any data on this block or this block, they will never be able to get this third hash. Then you create a third block.
Mm-hmm.
On this block, you hash all the data, which is a summary of all the data, fingerprint of all the data. But then you also include the previous block, this hash,
Mm-hmm.
which was already the hash of the other one. And then you hash them together until you get a third hash.
Okay.
So now you will never be able to produce this hash unless you have all the transactions from these 3 blocks in the exact same order. And it just keeps going like that forever.
Okay.
So this is how you determine the exact order of every single transaction in the blockchain and make sure that it's valid.
Got it.
Does that make sense?
Yes. So
Questions?
this is nothing but the Merkle rule, right?
Mm-hmm.
This is nothing but the Merkle tree. Right?
Yeah. Yeah. No questions about this?
No, that's no questions. We can move to next.
Okay. So that finishes consensus verification. Now we're going to look at computation and execution. So Bitcoin, the Bitcoin blockchain, it doesn't have any kind of computation or execution on it. It's only a database and ledgers. Ethereum has something called the Ethereum virtual machine, which is a sort of decentralized computation, which is maintained by thousands of computers and it's replicated across network, and it charges gas fees, transaction fees for each step. But the problem is it's inefficient because it tries to horizontally spread out computation to achieve one result. It can run software like dApps and smart contracts or even video games. So our client, they actually were originally a video game company. They had an Ethereum video game called Crypto Kitties. It was the most popular video game on Ethereum. But Ethereum, it didn't have the bandwidth to handle that many users simultaneously trying to use it. So they crashed the Ethereum network. When they did that, they decided to create their own blockchain, and that's where we are. Questions?
Uh, yeah, no questions. Yeah.
Okay. So networking, how does networking work? Identification and location of nodes is done by the network and it's stored in protocol data. The blockchain itself is the network, and it handles the networking functionality. On Bitcoin blockchain, it uses the gossip protocol, networking protocol, which is a kind of a P2P communication, and it's modeled after epidemics. So that I put a joke there, COVID protocol. Um, so that's how it works. But obviously, our client they use libp2p, and that's how they do networking between nodes there. Questions?
No. Okay.
Security, how does security work? So security on blockchains is one of the main things is through cryptography and cryptographic hashes. If you try to change any data on a cryptographic hash, the signature is going to be altered. It's done in SHA-256 hashing, which has 256-bit hexadecimals, and it creates a unique fingerprinted data along with write MD160. A message is hashed and it gives you a digest of fixed length, and it gives you digital signatures, private keys, block hashes, so on and so forth.
Yeah.
Another aspect of security in blockchains is decentralization. So you trust the cryptography and the technology, not individuals, and it's open source, so you can always audit it. There's complete transparency of records. Some of them have democratic decision making, tracking and tracing, confidentiality, the right to be forgotten if you don't expose your public key. It also protects against fraud because it's impossible to remove a page from a ledger from a block or to change it. And it will mean that your version of the blockchain will be incomplete and it'll be obvious that it's fraudulent, and it's also sustainable. Questions?
So, what is this right to be forgotten?
Right to be forgotten is just that you don't have to use your own personal information on a blockchain. So you don't have to have anything about who you are personally stored. You can have your money on there, transfer, send it to people, and nobody, unless you expose yourself, will be able to know who you are. So you get to retain that control over who you are.
Okay.
Unlike if you
But
have
actually, like, yeah. So, but when like we create any account in Coinbase or something, they ask for like all the details, right?
yeah,
So,
unfortunately, that's a problem with the exchange, but that's
uh-huh.
not you don't actually need that to make a wallet, and you don't actually need that to buy Bitcoin. You just need
Okay.
that to create an account on Coinbase.
Okay. Because like they verify like all the information, even they ask for driving license, all that.
Yeah,
Okay.
that's Coinbase, but that doesn't have anything to do with the actual technology. That's just
Okay.
that company.
Uh-huh. Okay. So they're not going to do anything with
Yeah, they do
like
that
creating the
for
wallet or their
American
own.
tax purposes.
Okay.
So it's kind of against the whole idea of Bitcoin and blockchain when they do that.
Uh-huh.
But they do that.
Yeah.
That's what they do.
So if is there any other exchanges like which doesn't ask for the personal details something?
Yeah, you can just go online and just get a wallet made. Now for an
Okay.
exchange,
Uh,
maybe you might have to use like local Bitcoin and like buy it from
mm-hmm.
somebody locally, or you would have to use one that's overseas. So
Mm-hmm.
most of the stuff that is accessible in English over here, they try to get your information because of tax purposes, but you can still find
Mm.
ways to do it.
Okay. Okay. Okay.
Are we ready?
Yeah.
Okay. So this is a diagram of a full transaction on a blockchain from beginning to end. So here we
Okay.
have the input and the output. The input refers to a set of transactions where Alice has Bitcoins that she wants to send. Output
Mm-hmm.
includes who she wants to send it to, the transaction fee, and to send the remaining money back to her account. So that when you put that together, that becomes her transaction message. Her transaction message, you add the private key to this. Then that creates a signature. The signature function is created from SHA-256 to make a digital hash. This is the digital signature, which signs the transaction, which is 256 bits. That goes with the public key. The public key will be verified along with the private key, and then it will see if it's true, if it's false. If the private key and the private key are false, then the transaction will not go through. If it's true, and the miners figure out, hey, that's a valid transaction, then they will go and update the ledger. The ledger now has Alice's transaction message to send money to Bob, along with her digital signature. And you can see there's other transactions here. Right here is the miner's fee. And then you have the nonce. And then they keep trying to solve the nonce while adding the transactions. When the nonce is solved, then there will be a certain number of transactions right here. The page will be done. Then the block will be added to the blockchain. It will have the hash of the previous block, the proof of work for the nonce, and all of the transactions. And then this is how it works. And then that information will get sent back to her wallet, and her wallet will be decreased. So this is a full transaction on a Bitcoin blockchain. Questions about this?
Yeah, this is very clear. And
Are you a visual learner? Do you like to look at diagrams?
sorry,
Are you a visual learner? Do you like to look at diagrams?
yeah, diagrams, like it makes a little bit easier to understand. So even like when you put the diagrams to explain things, it makes it easier to understand.
Let me know when you're done looking at this. You have
Yeah.
access, by the way, you have access to this. So you can
Okay,
always go into Google Drive and take a look at it.
Sure.
So that's it. We're done with the fundamental architecture. So we'll just look at some of the utilities and use cases for blockchain,
Okay.
Bitcoin, smart contracts, Ethereum, other use cases, and that's it. So we'll see if we can finish in the next 20 minutes. Bitcoin, Bitcoin is the first blockchain. It's created in 2008. It was released in open source in 2009. And it was the first decentralized cryptocurrency to use blockchain. It has an unspent transaction output, meaning that it has a maximum amount of Bitcoins that will ever exist, and eventually they'll run out. And every transaction is linked. There are scripts which validate the transactions. Only 1 megabit of data can be sent with each transaction, so very small, and it's non-refundable. Once a transaction is confirmed to be valid, that's it. It's decentralized, easy to set up, has anonymous and transparent usage, low transaction fees, relatively fast network processes. Mining, it's not really viable to mine on your own anymore. You have to probably do a pool mining with Slush or Ample. The tokens are decreased every 4 years, and eventually in 2140, there will be no more. It takes about 10 minutes to validate every new block. As the hash rate was increased, the 32-bit nonce was solved too quickly, so they increased the nonce. They created something called Coinbase transaction, which is an extra nonce, and the Coinbase wallet pays the miner previously non-existent Bitcoins. This isn't about Coinbase, the company, that's a aspect of the blockchain. They just increase the nonce. Questions?
Yeah. What is this unspent transaction output? That thing was not really clear. Like first decentralized cryptocurrency to replace open blockchain.
So
unspent transaction output. Yeah.
So when Bitcoin was first created, all of the Bitcoins that will ever exist were created right there. Then that was not given out. Every time a block is mined, some of that is given out. That's the unspent transaction output. And then eventually one day it will be done.
Okay. So still like some things are, some of the blockchain, Bitcoins are unspent.
Yeah, exactly. So you can think of it like this. When Bitcoin was first created, this amount of Bitcoin was there. Then the miners
Okay.
came and they
Okay.
started mining it. Oop.
Okay.
Every time they mine a block, it gets smaller,
Huh.
smaller until
Okay.
in 2140 is going to be gone.
Okay.
That's the unspent transaction output.
Oh. So after that, like, how we'll be able to buy, we have to buy it from some other person? That's
Yeah,
it?
you can only get it from other people.
Okay.
There'll be no more. So whatever is out there, that will be the maximum.
Mm-hmm. So that will create like a more demand kind of thing,
Yeah, it'll
which
be
will
high
increase the.
demand and low supply. Exactly. Yep.
Okay.
Ollie, who is this? You're talking Bitcoin here?
Oh man, Jim, I didn't even know you were here.
Yeah, I didn't want to interrupt. So
Oh man. When did you come on, Jim?
I don't know. What time is it? I don't know, 20, 30 minutes ago.
Oh yeah, really? I didn't realize that.
You were on a roll, man. I didn't want to interrupt it.
No, it's fine. It's nice to hear you, Jim. I can't see you, but hello.
Oh shit. I didn't realize my thing was off. So my bad.
No problem. Yeah, we're just oh man, I didn't realize. Yeah, we're just going talking about this stuff. I guess you were here for
Is
it.
it Bit? Oh, it is Bitcoin. Yeah. Okay.
Yeah, we're talking about Bitcoin. Yep.
Yeah.
Yeah, so I guess when he created it, the idea is that by 2140 that they'll have come up with some new stuff and
Okay.
they probably will phase it out. And if it is so, there will be a legacy thing. If the world is even around that long, we'll see what happens with climate change and stuff.
Given the way things are going today, you
Yeah.
may be right.
Yeah, I don't know if we'll be there, but we'll see. Any questions about this slide?
No, that's all.
Okay, great. So we'll talk more about smart contracts and Ethereum next week, but we'll just
Mhm.
go over it briefly.
Okay.
So a smart contract is a contract which is published on a blockchain. You can't do this on Bitcoin because you can only have 1 megabit sent with each transaction. So that's not enough data. But with Ethereum and other ones, you can. So what a smart contract is a contract that executes based on some kind of a trigger, some triggering event. It can either be an expiration date or a strike price or the selling of some physical asset or a date, whatever. The thing about smart contracts is that they can't be censored. They can't be rendered fraudulent because nobody can change it. They can't go down. They can't be misinterpreted because it's software. It's computer code which facilitates, executes, and enforces pre-agreed upon terms. So once you agree to it and you put it there and all the account balances with the public and private keys are listed, then that contract will execute. It's automated and it ensures consensual exchange of items without anybody in the middle. So you can agree to whatever terms you want in a smart contract. There's no government oversight. It's happening on the blockchain. So long as each person agrees to it, then it will happen. And there's also no need for legal language because it's written in code. Um, the kind of languages that you can write smart contracts in are Solidity, C++, Go, Python, and Java. So Solidity is proprietary to Ethereum, and we'll talk more about that. Go, the rest of them you know about. Our client also has one called Cadence, which we'll read about in the document. They have their own language specifically for smart contract and dApps, but it's based off of JavaScript.
Okay.
So the code defines the rules and the consequences, the obligations and the penalties. And so you code the contract, usually in Solidity if you're dealing with Ethereum. You put it on the ledgers, and then once the trigger comes, it'll be executed. Then the results will be agreed upon, and it'll update ledgers to record execution. So whenever a smart contract or a dApp is executed, it produces execution data, which is the result of that smart contract or that dApp. Questions?
No questions.
Okay. So we have Ethereum and then these other use cases. Okay. So we're gonna do a whole other course just on Ethereum. It'll probably take us three afternoons. Ethereum is a different blockchain altogether. It uses smart contracts and a different kind of node called oracles. It has a decentralized virtual machine, which we talked about, which executes scripts using public nodes. It was invented by Vitalik Buterin in late 2013, and it was funded by the sale of Ether in 2014. They had a public coin offering. It's written in Solidity, which is a combination of C++ and JavaScript. One of their problems was scalability, so they created proof of stake, which we talked about already. The initial version of the blockchain was called Homestead, and their final goal version is called Serenity. These decentralized applications were invented on Ethereum. They're called dApps. Most ICOs are on Ethereum, and Dapper broke Ethereum. That's why they created Flow. Questions?
No questions. Yeah.
Okay. So these are just some of the use cases that you can do with blockchains, supply chains, manufacturing. So you see supply chains, you'll see like certain kinds of food are recorded on the blockchain. Like for example, Manuka honey, you can see where it was, where it's been transferred to, who had ownership of it, manufacturing, automobile parts, wear and tear tracking, business processes, employee records, academic records, healthcare record keeping, cybersecurity, regulatory auditing, finances. Obviously, that's the whole point of blockchain. Vendor payment, asset tracking, inventory management, insurance claim settlements, machine learning, and land records. And so that's it. That's it. You have completed the first body of knowledge with the basics of blockchain. So hopefully this will start making the stuff which is in the architecture document clear, and then in these conversations that we're having, both internally and also with the client, that it should be a little bit clearer now, some of the concepts and terminologies that we're throwing around there about nodes, about peers, so on and so forth. And hopefully it starts coming together. So do you have any overarching questions about anything that we talked about?
No, not currently.
Okay. So I know you said you're still making your way through the document. You didn't get a chance to read it today. That's fine.
Yeah,
Just
yeah.
try to have it done by next Monday.
Yeah.
And then when we do the Ethereum slides, that will start making it clearer. But I want you to be able next week to start going through the code base, start reading the code base. And when you read the document, you'll see what we're focusing on in specific. And then also as you sit in to the meetings, we also have a meeting tonight at 8 o'clock, which is going to be the retro 8 o'clock Eastern time. So in 1 hour, in about an hour from now, we're going to be going over the sprint. So you get to hear Sean and Miklos talking about kind of what they saw, what was going over. So I want you to be able to start going through the code base next week and start interfacing with Sean and Miklos, so they can kind of show you where the pitfalls are, what to avoid, what changes that they're working on. And then we'll go through the Ethereum slides, and maybe mid next week to end of next week, I would like you to start actually doing some development work. Obviously with Sean and Miklos involved, and we'll figure out where you want to go. So we're trying to write some automated tests. We want to write our tests for the modules that we're writing beforehand. So I'm working on like the high level overview for the tests. Sean is helping me with the test automation, but probably one person is going to work with me to finish writing the test beforehand, and then the other two engineers will write the code to pass the test. So we'll see how that ends up playing out. But on a heavy sprint, you guys just might all three of you might just end up working on the same thing. We'll see what happens.
Okay.
So any questions about the direction that we're going, what you need to be focusing on and learning?
No, actually, like what we do usually the other way, which is like a reverse way. Like we write the code first and then the unit test or the integration test. But here, I think like we are going the right direction by writing the unit test and then the code. So for writing the unit test, like we will have all the details, like the functionality, everything, right?
Yeah, so I'm gonna
So
define the full functionality for what the new module should do, and then we'll write the unit test according to that definition, and then write the code. Exactly.
okay, sure.
Yeah.
So yeah, initially like we'll be writing the test, but how we will make sure the test, like what we are writing, is correct or not, based on the functionality you write.
So we're gonna use Ginkgo. Are you familiar with Ginkgo?
No.
It's a BDD. It's a behavioral driven development platform. So I'll send you some
Okay.
information on it.
Okay, sure.
I'll send you that in Slack. Just give me 1 second.
Yeah.
You can take a look at it. So they do have unit tests already, the client, and we're working on updating those to work on the code that we're using, so that we do have some model tests to use, but we want to automate them to where I can write the behavior and then somebody can sorry, give me 1 second. I'm sending you. So I just sent it to you on Slack. That's Ginkgo right there.
Sure.
Let me see.
Also, we are going to use gRPC for the peer-to-peer communication, or
Yeah, that's for the APIs, the
Okay.
RPC. So you'll see
Okay. Is it
the whole discussion for that in the document.
okay? So we are using gRPC for the lib P2P, or
No, so the lib
just for the
P2P,
APIs?
the lib P2P is for node identification and for the nodes to communicate on the network. The gRPC is going to be specifically for the APIs to send and receive information from one another after
Okay.
connection is established between the various nodes on the network.
Okay. Got it. So node can be a client or node can be a server. They will be calling each other.
Exactly. Yep. But they need the lib P2P to find each other first.
Got it.
So I just sent you the GitHub on Ginkgo. Jim, did you see that on the Elastic Dapper external that Peter sent a question at 3 o'clock? He said, sounds like you're doing some more testing before we review it. Any idea when you'll be ready to share the PR?
I did not see it yet. No.
Yeah.
They're trying to run the testing on it right now on GCP. So hold on a sec. Where did he put that in the group channel?
Yeah, the very first one on Elastic Dapper Con.
Okay.
Yeah, nobody responded to him. So I don't want him to just get like left-handed like that. Maybe they didn't respond to him on purpose. I don't know. So, gentlemen, I have to run and do something real quick before our next meeting. Stop the recording.